In the last video, we talked about fixed or clamped boundary conditions for our string or sound waves in our tube. So let's talk about another alternative, which is free or open boundary conditions. So here, the idea is, if we imagine that we have a string, we're looking at standing waves on the string where the ends are free to move up and down and flop around. Unfortunately for a string, it is basically impossible to keep tension on the string and simultaneously allow the ends to freely move up and down with no force in the up and down direction. So when we're talking about these examples, it turns out to be generally easier to think about this for sound waves. Although, on paper at least, it would apply equally well to strings. So the idea here for sound waves, I guess I should say, so this is, we're talking about free end boundary conditions. Also called open ends if we're talking about a tube. So this could look like something like this. So let's say we have a tube with one end open and one end closed, right? Hollow tube. So this end has like a cap on it or something. This is hollow. You could stick your finger in there or whatever. So our standing waves are going to have to reflect what's going on at these boundaries. Remember, before when our string was clamped at the end, we said, oh, well, if our string is not moving there, that has to be a node of our standing wave. It turns out, so that is still going to be true for the closed end of the tube. This is still going to have to be a node of our standing wave. Where there's an open end, where it's free to move, mathematically, we can show this if we had more time and really wanted to. We can show that this end has to be an antinode. And the same would be true if you had, a floppy end of a string allowed to move up and down freely, but we'll just think about the tube. So the tube has to have an antinode at open ends. So this is, in contrast to our closed end. So here, closed end means a node, there's no displacement. Here, an open end means there's an antinode, that is where we have our max displacement. So in the case of something like a sound wave, this is the maximum motion of air back and forth in and out of the tube at that point. All right, so we can have different combinations of open ends and closed ends, right? We could have a system, we already have done the math for a system with both ends closed, right? So a tube with sound waves where both ends are closed is going to have a node at either end, and we already know what those standing waves look like, right? We can also have a system with one end open and one end closed, as I've drawn here, or we can have a tube with both ends open that has to have an antinode at both ends, and we're going to look at both of these cases and look at the standing waves we get from that. So we'll start with one end open and one end closed for no particular reason. So here's my tube. We'll say again, this is length L. This end is open on the right, this end is closed on the left, which means my standing waves will have to have a node here, and they will have to have an antinode here. So the fundamental mode, the lowest frequency we can have, is going to have a standing wave pattern that looks like this, where this is our antinode on the right. So it turns out this is, not only is this not a wavelength, it's not even close to a wavelength, right? If we were to continue drawing what this wave looks like, it would, it's going to go up and then back down to 0, and then down and then back up. So what we're really looking at here is, kind of had to cram it in on the right, but we're really looking at like 1/4 of a wavelength. Or you can also imagine, if you have a node here and an antinode here, symmetrically, there would be another node over here the same distance L away, and that distance is half a wavelength, the distance between two nodes. So anyway, the point is, on this diagram, this distance between the node and the antinode is not lambda over 2, it is lambda over 4. And that's something you can, I mean, I'm not going to ask you to prove that. That is something you can use in these problems. Distance between a node and a neighboring antinode is always lambda over 4. Okay, so anyway, if L equals lambda over 4, that means lambda is equal to 4L. So our wavelength is this long for our tube with one end open and one end closed. All right, so for this same tube, we can also have a standing wave that looks like this. Where here we still have a node, we still have an antinode over here, and now if we think about our distances, this distance between the two nodes, using our usual rule, is still lambda over 2, and now this distance is 2/3 of our length L, right? So if we take this length L and split it into 1, 2, 3 equal pieces, this is 2/3 of those. So lambda over 2 is equal to 2/3 of L, which means lambda is equal to 4L over 3. All right, we'll do one more and see if we can spot a pattern. This one's not as even, but I think it's good enough to get the idea. So, so here, the distance between these two nodes is still lambda over 2. And now, if we look at how L is split up, we have it split up into 5 equal parts. 1, 2, 3, 4, 5. So lambda over 2 is 2 of those 5. Lambda over 2 is 2/5 of L, which means lambda is equal to 4L over 5. So for our systems with one end open and one end closed, we go 4L, 4L over 3, 4L over 5. It turns out that lambda is equal to 4L over n for odd values of n only. We can never have the even values of n. All right. Great, let's look at a system with both ends open. So here, if we have a tube with both ends open, that means it needs to have an antinode at both ends. So we'll still assume this is length L. So an antinode at both ends is going to look like this. This is what the fundamental frequency looks like. So here, we could do this a number of different ways. One way you can see this is still our lambda over 4, so this is half of a wavelength. You also can use the fact that between two adjacent, sorry, these are not caps, I'm just marking distances here. Between these 2 points, that is between 2 adjacent nodes, is also lambda over 2, just like how between 2 adjacent antinodes is also lambda over 2, just the same as we have used previously between 2 different nodes. So here, L is equal to lambda over 2, so lambda is equal to 2L. Our next standing wave pattern looks like this. So here, let's try to draw this a little more symmetrically. That's a little better. So here, we have an antinode and an antinode and an antinode, right? So we know that this distance, as we saw above, this distance is half a wavelength, this distance is half a wavelength. So my half wavelength is half of my L, which means lambda is just equal to L. And my next one looks like this. So now between antinode, 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 I have 3 of these That is lambda over 2. So 1/3 of my length is lambda over 2. Lambda is equal to 2L over 3. These are actually exactly the same as what we had for the two fixed ends. So for a system with two open ends, it turns out the standing wave wavelengths and frequencies are the same as if both ends are fixed. Or, in the case of the tube, they're the same as if you had, standing waves are the same as if you had a cap on both the ends. All right. So we'll do some examples in a future video, but hopefully this gives you some sense of how to think about these systems, how to look at the diagrams, and how to identify what's going on in the diagrams. But really in all of these, the most important fact, other than being able to draw or recognize the pictures, is the distance between nodes or between antinodes is lambda over 2. This is really the key to all of these sorts of problems.